All right, I guess we can start. So let's recall what we did last time. We started with our Kitaev chain in one dimension on the lattice, and then we learned how to take the continuum limit of that model, and we learned that it corresponds essentially to a one-dimensional Majorana fermion with an inverted sign of the mass. And using that formulation, we were able to place the theory on an arbitrary manifold and compute the partition function. And we saw that the partition function is related to the number of zero modes of a two-dimensional Dirac operator on that manifold. And okay, it depends on the manifold and the spin structure. And we discussed that it's a topological invariant. Remember, we had this argument: as you change the metric, the levels of the energy levels of d slash, the eigenvalues of d slash move around, but n not always changes in multiples of 4. But actually, this expression satisfies a much stronger property. It's not only a topological invariant, but it's also a bordism invariant. Topological invariant, I mean, of the manifold. So this turns out to be a bordism invariant. So I'll explain in a second what bordism means and what a bordism invariant means. But for the proof of this statement, just follows from the Ataya-Patodi-Zinger theorem. And actually, the APS papers are not too difficult. You can actually read them. There is a paper by Witten that explains some of this stuff. And you can also look in Nakahara's textbook, Geometry, Topology, and Physics, where he also discusses the APS theorem. But now, let me actually say what bordism is. So, kind of going to go into the realm of topology for a little bit. So consider closed D manifolds XD and YD. We say that they are bordant. Bordant if there exists a D plus one dimensional manifold MD plus 1 such that the boundary of this manifold is equal to XD union YD with its orientation reversed. So let me, the famous picture is, say you have two circles, right, and you can draw a pair of pens like this. So this is Y at the bottom, this is X on the top, so here Y is just a single circle, X is two circles, and there is the pens are this two-dimensional manifold.
What is Y?
It's Y with its orientation reversed. So if you want to keep track of orientation. Okay. And we say that Z of X is a bordism invariant if Z of XD is equal to Z of YD for X and Y which are bordant. And it's actually believed that bordism invariants classify invertible topological phases. That was initially conjectured by Kapustin and made rigorous by Fried and Hopkins. Okay, so a few more words about this bordism. So bordism defines an equivalence relation on manifolds. And now manifold subject to this equivalence relation can be endowed with a group structure. How? Well, so D manifolds mod the bordism equivalence form an abelian group. Abelian group. So what's the addition operation in this abelian group? It's just the disjoint union of two manifolds. Right? So say this is X, this is Y. So this joint union of them is the addition. The zero is the empty set. And the inverse is the manifold with its orientation reversed. Right? So X disjoint union with X bar is always bordant to the empty set. So just to illustrate this fact, let's draw. Right, so here I have X, here I have X bar, and here I have nothing. So X union, disjoint union X bar is bordant to the empty set. Okay, so I claim that for an invertible theory, the partition function is a bordism invariant. So we are going to, maybe later in this lecture, we are going to try to justify that. So, but for now, let me for invertible topological quantum field theory, Z is a bordism invariant. Here, by TQ of T, I really mean that the partition function doesn't depend on the metric. Yes?
And do you also assume that it's a unitary TQ of T?
So I think in the proof that bordisms classify invertible phases, unitarity played an important role. So in Denfried's proof, maybe someone will correct me. Okay.
Max, I'm going to explain what you mean by invertible TQFT.
So we discussed what it means to be an invertible phase.
Yeah, that you did.
So somehow invertible TQFT is a continuum limit of that. Okay, so at the very least, what we want is the ground state on an arbitrary spatial manifold to be unique. That's what we are going to demand. Okay, and so if the partition function is a bordism invariant, well, actually, it will be a homomorphism from this bordism group to complex numbers, right? The partition function is a complex number on a general manifold. So actually this abelian group, let me denote it as omega d. So this has to be a homomorphism, that is z of x disjoint union y has to be z of x, z of y. Why homomorphism? Well, we want this property to be satisfied, right? If I have a disjoint union of two manifolds, then the partition function should factorize. Now, one place where we have where unitarity enters is, in general, for unitary theory, the partition function of a manifold is the complex conjugate of the partition function of the manifold with its orientation reversed. So then, from this, we expect for the empty set the partition function is 1. So, but empty set is x and is Borden to x disjoint union x with its orientation reversed. By the homomorphism property we have this, and then by unitarity this is z of x squared. So that means that this is actually a map not into complex numbers but into unit circle.
I don't understand.
Sorry?
Are you proving this or assuming this?
No, so this is a general statement that if you reverse the orientation, the partition function complex conjugates, and then assuming this and assuming this natural property that why is this natural?
Yeah.
Well, you have a partition function on two disjoint manifolds, right? So you have some degrees of freedom here, you have some degrees of freedom here, so you independently sum over, so you should have a product.
No, but here you're using the fact you haven't yet shown that the partition function is importing with.
That's the key non-trivial property, which I'm assuming for now, and later in the lecture I'll say a few works. So yeah, so this is an assumption. No. Eventually, I'm going to give an argument explaining if I have time. I'm just listing the consequences of that for now. Okay. Now, well, a little bit about what kind of manifolds we work with here. So, on manifolds, you can put various structures. And depending on physical type of theory that you are interested in, you'll study bordism of manifolds with different structures. So if you just want plain vanilla phases of bosons with no symmetry, then you study bordism of manifolds with orientation. So oriented bordism. Let me see. Here. So, bosons, no symmetry. You only know how to put your theory on an oriented manifold. If you don't have time reversal symmetry, you don't really know how to put the theory consistently on a non-orientable manifold. So you only study oriented manifolds, and you study bordisms of oriented manifolds, which is denoted as omega SO. SO because that's the that's the structure group of the tangent bundle.
So when you write this plot, this x bar, could we already assume that
Here, when I gave this definition, I actually assumed that we are dealing with oriented.
But there is a more general definition of bordism.
So for each structure that you want to preserve on your manifold, there is a separate definition. Oh, so say if you're dealing with unorientable manifolds, then there is, okay, actually, let me think for a second. There is no notion of orientation reversal, but you still have an inverse. Yeah.
What it is?
Sorry?
And what it is?
What is the inverse of a general
Non-invertible?
non-orientable
Non-orientable, yeah.
manifold? Yeah. I'm wondering. I think it's just the manifold itself, right? Because then it doesn't matter that you just play this trick with, you think of X cross I, and then you just think of of I as you start with this, with X cross I, and now you just do this. If you're not keeping track of the orientation, then you're fine.
Sorry. And an orientable manifold always has like a orientable double cover, so maybe that's what.
No, but we don't want the double cover. We want. I think the inverse of a non-orientable manifold is just.
Yes, that's what I'm trying to say.
It's just itself.
Is it not just a consequence of the fact that it's always a double cover? You can always go to a double cover that is orientable. Is that equivalent?
I think this is easier. You just forget about orientation, and then this.
So then the bordism group is always powers of G2?
That's right. Okay, so that's bosons with no symmetry. What about if you have fermions with no symmetry? Well, if you want to put fermions on a manifold, as we already discussed, you need a spin structure. So then we'll be dealing with bordism of manifolds endowed with spin structure, and we would like the manifold that connects the d plus one dimensional manifold to also have a spin structure that restricts to the spin structure of the two manifolds X and Y on its boundary. Okay, what if we have theories with unitary symmetry? Unitary symmetry, unitary internal symmetry. Symmetry. G. Well, then you can couple your theory to background G gauge fields. Again, I'll draw this picture. So you'll have on your X, D, and Y, D, you'll have G bundles defined, and for so now you consider bordism of manifolds with G bundles, and which is basically a G gauge field, and then you require that the interpolating manifold here, MD plus 1, also carries a G bundle that restricts properly on the boundary, right? So that's say you're dealing with bosons, then this is known, this bordism group of manifolds equipped with G bundles is not, you can write like this, where, well, you can think of a G bundle modular gauge equivalence as a map to what's known as the classifying space, BG of the group, but for our purposes, just think of it as bundles equipped with gauge fields living on them. Okay, so suppose you want to do time reversal. for phases with bosons. So just Z to T. Well, now time reversal allows you to put your theory on a non-orientable manifold, right? You know how to, if your orientation reverses under pi change, you know exactly how the fields transform under that orientation reversing transformation. So this allows you to put the system on a non-orientable manifold. And now you consider bordism of general manifolds, possibly non-orientable, and you forget about orientation. So this group is known as omega dO, where O is now, again, just the OD group of symmetries of d-dimensional tangent space. Okay.
Sorry, can I ask a question?
Yeah.
Can the SO structure or the spin structure have an interplay with the G symmetry when you have symmetry?
Yes, yes, it can. In particular, you know, physically important situation for fermions is when you have your symmetry group of your system includes as a subgroup the fermion parity, right? So then you can mod out by this fermion parity. This is the bosonic symmetry group, and then this is the Z2F, the fermion parity, right? And you know, this is the full group, and then these bundles on your space that you consider, well, it's kind of a twisted spin structure by this GB, and so there is a corresponding notion of bordism then again. Yes?
The G symmetry here is assumed to be a zero form symmetry, I guess?
Yeah, everything is zero form in my lectures. You can talk about classifying invertible phases with high form symmetry. People have talked about that, but we have enough on our hands just with zero form symmetry. Yes. Okay, so that's time reversal, and you know, for fermions you can also add time reversal. You can have time reversal that squares to +1 or -1, -1 to the f, that is, fermions with time reversal. Well, you have typically two choices: either t squared in real time is -1 to the f, or t squared is just 1. And this corresponds to placing the theory on a pin plus, what's known as a pin plus manifold. So you have a pin plus structure, which is kind of just a lift of OD to some covering group. And then for t squared equal +1, it's omega d pin minus. So again, you consider bordisms of manifolds endowed with either pin plus and pin minus structure. And you know, this classification, this kind of bordism classification appears to really work. You know, when you play it against things that are known through other methods, say from analyzing models on the lattice or from other field theory arguments. So let's see it in action. Let's see. Let's go here.
So I have a question.
Yes.
Is it obvious what the inverse should be in the bordism group in the fermionic case?
Yeah, so there is a notion of inverse of the spin structure.
I see.
Yeah. So let's do this. So the case we are very familiar with by now, fermions in 1+1 dimensions with no symmetry. That is, with only fermion parity symmetry. So you can ask what is the spin bordism group in 2 dimensions, right? That's the right question to ask, as we discussed in this case. And turns out that this is Z2, and this Z2 is generated by a torus with a Ramon-Ramon or periodic spin structure, right? So it's torus with periodic boundary conditions. So, if you choose any other kind of boundary condition on the torus, then you can fill it in with a 3-dimensional manifold. Say you have periodic spin structure along one direction and anti-periodic along the other, then this direction which is anti-periodic you fill in like this with a solid donut, and turns out that now the spin structure on this solid donut will extend to the boundary, or when you restrict to the boundary, you end up with anti-periodic spin structure along this direction. But if you have periodic on both cycles, then there is no way to fill it in, preserving the spin structure. So, okay, so from this bordism classification, we can now do the cobordism classification, which means we think about maps from this bordism group to complex numbers. And the non-trivial, so there is a trivial phase that just to every manifold assigns one partition function. But the non-trivial phase, which will be precisely the Kitaev phase, will assign to this torus with periodic or with Ramon-Ramon spin structure, will assign -1. Right? That's a homomorph. This is a generator of a homomorphism from Z2 to C. And to torus with other spin structures, it will assign +1. And we saw that that's exactly what the Kitaev chain does, right? So we've recovered the Kitaev chain here. Yes?
Sorry, how do you know that group is Z2?
Because mathematicians computed it. Yeah. So generally, in general dimension, the calculation of various bordism groups, especially when you twist by some unitary symmetry G, is actually a highly non-trivial problem. So these groups, omega d SO, omega d spin, omega d O, and I think the pin ones are known in any dimension. But once you add G and you start, okay, so also omega DSOBG is known, say, for G like Z2 or Zn. But if you start kind of twisting spin together with unitary symmetry, it gets complicated quite fast. So, yeah.
Is this also the case when G is continuous?
Actually, so people believe that this classification also works for continuous groups. Yeah.
Sorry, I have a question. What about if the G group is not on site?
Well, so here we only talk about on-site symmetries throughout these lectures. Reflection is an example of a non-on-site symmetry where this also works. So to do reflection rather than time reversal, in Euclidean spacetime doesn't matter whether you're doing time reversal or reflection. So reflection you can also do. And then for lattice symmetries, people believe that there is this crystalline equivalence principle that relates classification of of invertible phases, or in fact any gap phases with point group symmetry or lattice symmetry to that with internal symmetry. Okay, so we recovered our Kitaev chain, and this classification tells us that there is no other non-trivial phase for this dimension and symmetry group than the Kitaev chain, and that's also we know from it's basically a theorem in one dimension on the lattice. You can prove it. What about bosons in 1 plus 1D? Bosons in 1 plus 1D. Okay, so what's the relevant group? Bordism group. Omega. Bordism of two-dimensional manifolds with orientation. And this group turns out to be trivial. This one is actually easy to understand, right? Any two-dimensional oriented surface, you can fill it in with a three-dimensional bulk. So any two-dimensional oriented surface is bordant to a point, is a boundary of some three-dimensional manifold. So no non-trivial phases for bosons in 2D without symmetry. And again, we know this from lattice. It can be proven on the lattice. Okay, let's see. What about bosons in 1 plus 1 dimensions with time reversal symmetry? Bosons in 1 plus 1D with T symmetry, Z2T. Let me write it like this, Z2T symmetry. Okay, so what's the right bordism group? Well, time reversal symmetry allows us to place our theory on non-orientable manifolds. So we do this, we compute this bordism group omega d equal to O. And this turns out to be Z2. And it's generated by RP2, the real projective plane in 2 dimensions, which is, you can think of as a sphere with its antipodal points identified. Okay, so the non-trivial phase assigns to this RP2 -1 partition function. And again, this classification agrees with the theorem proved on the lattice, and this non-trivial phase is what's known as a Haldane chain, or Haldane, or sometimes people there is another name for this, not Haldane, but AKLT, Affleck plus.
Haldane chain may be for any integer string, so AKLT may be more accurate.
Well, if you think of it as a phase endowed just with time reversal, right? So then.
But Haldane chain for spin 2 is trivial.
Oh, okay. Spin one.
Refer to integer spin.
Okay.
AKLT may be more accurate.
Let's write AKLT. Okay, what about fermions in 1 plus 1 dimensions with time reversal symmetry? Fermions in 1 plus 1D with T squared equal +1. You already had a lot of fun with this kind of problem yesterday in the exercises. Remember, we were thinking about k copies of the Kitaev chain endowed with a time reversal symmetry that squared to +1. Okay, and so what's the right bordism group to compute here? Omega d equal to pin minus, right? Because I have T squared squaring to +1. And turns out that this bordism group is Z8. And remember, in your homework you showed that 8 copies of Kitaev chain are trivial. And so the Kitaev chain is exactly the one that generates this. Well, what is the partition of the Kitaev chain? Partition function of the Kitaev chain? It assigns to so first of all, what is the generator of this bordism group? It's again RP2. And RP2 has 2 pin structures, which differ just by twisting along the single non-trivial cycle of RP2. And so nu equal 1, so single copy of Kitaev chain assigns to RP2 either plus or minus 2 pi I over 8, depending on the spin minus structure. And if you have k copies, you just assign 2 pi k over 8. So when k is equal to 8, that's trivial. And there is nothing other than the Z8 that's generated by the Kitaev chain. And we also know that from the lattice. So again, this agrees with the lattice. Okay.
Yeah. Should I think of these as like fractional number of zero modes for the Dirac operator or something like that?
Oh, you're asking how, before we had this partition function which is equal to -1 to n naught. So you can do the same calculation now on a non-orientable pin minus manifold. And there you learn that when you do this ratio of partition functions with positive and negative m, it's not only the zero modes that contribute, but the entire spectrum. And what matters is actually the spectral asymmetry, or the so-called eta invariant. And the eta invariant turns out to be quantized in this 1 over 8 units.
For question, so is it possible to classify this based on the lattice, like construct the RP2 effect on the lattice?
People have various tricks, so-called partial transpose and so forth, for diagnosing this on the lattice, so kind of mimicking RP2 on the lattice. Yeah.
The stacking is kind of the mirror image of like the disjoint union in this bordism.
Let me think for a second. Stacking is a little bit different, I think. So stacking is is like a tensor product of your two invertible theories. Sorry, I did the question. Yeah. So so you have one invertible theory, Z1, that assigns something to a manifold XD, and you have another which assigns something to the invertible manifold, and then the stacking Z1 plus 2 is just Z1 is this operation, just product of the two partition functions.
So I would imagine that you are imposing the locality to the invertible TDOT. So
that's right. Yeah.
So but what you get there is a bordism, which looks very global. So is there any remnant of locality here, or is it kind of gone when you go to the classification?
You're again asking why does bordism classify local, invertible? Yes. So I'll give you an argument shortly.
Okay, great.
So maybe last few examples kind of proving the success of this bordism classification. So actually, example that Thomas discussed. Fermions in 3+1 dimensions with t squared equal to -1 to the f. So here, if you just classify non-interacting fermions, so basically classify band structures with time reversal symmetry, you learn that the non-interacting classification is integers. Similar to the 1 plus 1D fermions with t² equal +1, where we saw that without interactions, any number of Kitaev chains is a distinct phase. So here, the generator here is so-called topological superconductor, or you can, as Thomas explained in the continuum, you can think of this as a Majorana fermion with an inverted sign of the mass. And if you only allow yourself to write down kind of quadratic theories in fermions, then the classification is integers. Okay, so let's see how the bordism works. So we are supposed to compute bordism of 4 manifolds.
Sorry, but for him it was not integers. For him it was Z2 for Thomas.
So let's discuss in a second. So omega d equal 4 pin plus. So this is this group turns out to be Z16, and what is it generated by? Generated by RP4. RP4 again is a sphere with antipodal points identified. It has 2 pin plus structures, and the generator. So the classification is now broken by interactions to Z16. The generator assigns to RP4 e to the plus minus 2 pi I over 16, depending on the spin structure. Now you can ask, how is this related to Thomas's gravitational theta term? So it turns out that for the generator of the Z16 cobordism group, you can detect it already on an orientable manifold, in particular on something like K3. If you look at k equal 2, so 2 copies of this, you can only detect it on non-orientable manifolds. So if you put k equal 1 on zk equal 1 on manifold which is orientable x, then you get this. I'll just write it like this. I'll write it as 2 pi I over 16 times the signature of the manifold, and the signature is exactly that expression that Thomas wrote with an integral of trace r wedge r. So the orientable. So for k equal 1, you can already detect it on orientable manifolds. For higher k, right? So you take k copies. If k is even, you cannot detect it on an oriented manifold, but you can detect it on a non-orientable manifold.
But in his case, just if you have 2 copies of his system, then we can get the trivial because we can't interact fermion. So why is it not just Z2?
You can get what trivial, sorry.
So he had a single well fermion. If you take 2 copies of his system, then isn't this just a trivial phase?
Depends on how time reversal acts on those copies, but no. So you can think about the boundary here. The boundary turns out to be a single Majorana, 2 plus 1 dimensional Majorana, gapless Majorana. So something like chi transpose C dagger D chi, and chi goes to I sigma y chi under time reversal to minus I. So there is actually, if you write down only quadratic mass terms for any number of flavors, you cannot gap it out. You cannot gap out the boundary. I don't know if I can do it on the fly. I can.
What's wrong with the usual particle physics way of writing Dirac mass terms?
You break time reversal.
Not that I know. I mean, the usual free Dirac fermion is time reversal invariant in the absence of external magnetic field.
I think that. Okay, so first of all, are we talking about 2 + 1 dimensional, or are we talking about 3 + 1 dimensional? So for 3 + 1 dimensional theory, Thomas also wrote down a mass term. It's just that the mass term had a.
That was a special mass term for a wild fermion.
That's right.
But I'm now talking that if you take 2 copies of his system, there will be just 2 wild fermions. I could write a different mass term, which would be a Dirac mass term.
That will be. It's not that you cannot write down trivial phases. Is that you can write down mass terms that will not be continuously connected to a trivial choice of mass terms.
So to write the mass term that he mentions, I think you have to take the second Fermi to transform with the opposite sign. So the anomaly cancels and you can gap it out. But if you impose both to transform with the same sign, the mass term becomes gone.
Well, it's also about whether it's in the bulk or on the boundary, right? So on the boundary, if you have all the Majoranas transforming in the same way, then you cannot write down a mass term. If one of the Majoranas transforms with plus here and the other with minus, then you can write down the mass term.
Why is it useful then? I mean, I would like to have classification of phases which would somehow. Yeah, I'm confused. Because until now, particle physics and condensed matter were going hand in hand, but here we seem to have a deviation.
No, I don't.
So you're saying that Dirac fermion, massive Dirac fermion, is not a trivial phase.
It depends what symmetries you impose.
It's a Dirac fermion. It respects time reversal invariance. Free massive Dirac fermion respects time reversal invariance. You're saying, oh, that's not the time reversal invariance that I like.
But it's just it can be a trivial phase, right?
Yeah, it's a trivial phase.
So trivial phases, it's fine if you realize a trivial phase, but you can also realize a non-trivial phase. That's the point. So usual massive Dirac fermion, if you m psi bar psi, time reversal acting in the usual way, if you don't insist on U1 symmetry, then both signs of the mass are the same phase. But you can make time reversal symmetry act on the left. Okay, now if you write it in terms of whiles, say two whiles, each one massive, and if you choose the same transformation property for the 2 whiles, then 2 is non-trivial.
Maybe it would be helpful to say that the distinction is between whether you use T and CT. I think that's the mismatch between you two guys.
Right. So if you, okay. So in this case, if you think about CT,
there's no Z16, right?
There is a Z. Z. So if you use T, which is semi-direct U1, then this generates a Z2 phase if you keep U1, and trivial if you don't keep U1, if you don't exist on U1. If you look at CT cross U1, then if you then inverting the mass changes the phase, and it's actually a Z8 classification. The free fermion generates a Z8. So it depends how the symmetry is chosen to act. quite subtle. So these higher phases that are only detectable on non-orientable manifolds are pretty subtle. Maybe there is a simpler example, right, with the Kitaev chain, where we had, the edge Majoranas. If they all transform in the same way under time reversal, then you cannot gap them out. If they transform oppositely under time reversal, then you can gap them out.
I started getting confused when you started writing this subscript in the partition function, because I thought it was homomorphism from bordism to C.
Yes.
So what is the subscript?
So there are different homomorphisms that you can choose, and this is like, it's like the, what is it? Dual. It's dual of the bordism group. So the maps from bordism group to U1 itself is itself a group, and then I'm labeling the elements of that group.
Oh, okay.
Yeah. Okay, so we have this interesting Z16 in this case. So I could go on, talk about U1 cross T. I could talk about these examples, but let me stop with this zoo and talk a little bit more generally. Right, so more generally, we have a bordism group, right? It's an abelian group. So I can write it as some kind of direct sum of torsion terms plus free terms. Okay, so, and now I need to choose a homomorphism from this to U1. Well, I can choose homomorphisms from Zn1, say from Zn to U1, as we kind of already alluded to. I can have n different homomorphisms, 2 pi I k over n, k running from 0 to n minus 1. So in the classification, each of these torsion groups will give me also a Zn in the classification.
Sorry, is it obvious why the bordism group should be finitely generated?
No, so there are examples when it's not. So that's why I wrote here plus z to the m, where z. Oh, you're asking whether you can have infinitely many. I think they are finitely generated, but I don't know of a proof. Maybe someone knows a proof. Yeah. Okay, so what about these free factors here? So, okay, what about homomorphisms from integers to U1? Okay, so I can assign to the identity in Z, I can assign any phase theta. So do these choices of theta correspond to different phases? And the expectation is that no, right? Because you can tune theta continuously here, right? So this is some family of states, but they are continuously connected. So these Z's here do not correspond to invertible phases. In d dimensions. So from what we have up till now, we have that I'll say TQFTs, invertible TQFTs in d dimensions are classified by torsion of the bordism group in d dimensions. But remember, when maybe in the first lecture, I gave you.
Sorry? I mean, I said there are declassified.
That's right. So in the first lecture, I sketched the classification of phases without symmetry in low dimensions, and there were in 2+1 dimensions there were phases which had an integer classification, which I called the p+ip superconductor, and the for fermions, and the E8 state for bosons. We know that e.g. fermions in 2+1D, we have an invertible phases are classified by Z. So where does this Z come from if everything is torsion? So let's actually discuss that particular state. So we call it, in condensed matter, we call it a p+ip superconductor in 2+1D. You can think of it as a 2+1 dimensional Majorana with an inverted mass term. It's a free fermion state, and as I told you, all the free fermion states can be thought of as Majorana or Dirac fermion with an inverted mass term. So here, the bulk Lagrangian is something like where now I'm in 2+1 dimensions, so there are 3 gamma matrices, and as a reference, I take the trivial phase to have m equals 0. To have positive m, the non-trivial phase to have negative m. If I consider a domain wall between positive m and negative m, I find that I have a chiral Majorana mode, 1+1 dimensional chiral Majorana mode living on it. Right? So this is x, this is y. M greater than 0, m less than 0. You'll find that you have a Majorana mode, so boundary L. I'll just have chi right d tau minus I dx chi right. So just right mover. So C equal 1/2 right mover. So this has a gravitational chiral anomaly. Same calculation to find the 0 mode as you did in your homework last yesterday, except you just add the momentum along the y direction. Okay, so very good. So we can now play the same game, and we can compute the partition function of this free fermion theory with an inverted sign of the mass on an arbitrary manifold. And I will not go through all the details as I did for the Kitaev chain, but it's very similar. So Z, you take Z of theory with negative mass divided by Z of the theory with positive mass. Okay, so then you need to take the Pfaffian of this operator. Pfaffian of C dagger D plus M or minus M over Pfaffian C dagger D plus M. The sign ambiguity cancels between the numerator and denominator. Again, all levels come in pairs because of this anti-unitary symmetry. Ck squared equal -1 of the Dirac operator. So we get some product over eigenvalues of I lambda minus m over I lambda plus m, where lambda are eigenvalues of minus I d slash, and this is the Dirac operator on the manifold. Now, the difference from the Kitaev chain that we discussed last time is that while the eigenvalues come in these Kramer's pairs, there is no relation between the eigenvalues with positive lambda and negative lambda. So this is, in general, is some phase that you really need to compute. And, well, the computation is easiest in the limit when m goes to infinity. So you can think of, so this positive m and negative m are representatives of two phases, and as I increase m or change m, well, because I'm in the same phase, I expect that the partition functions will only change by local counter terms. So if I don't care about local counter terms, I might as well take m to infinity. So now I compute this limit as m goes to infinity. I think also related to a question that Shaugan asked last time. And I get the following expression. I get the spectral asymmetry of the Dirac operator, which is defined there is a contribution from the number of zero modes eta of minus I t is the number of zero modes of the Dirac operator. We are already familiar with this from the Kitaev chain. But now there is another contribution, which is called the eta invariant, or the spectral asymmetry. And it's obtained by essentially counting +1 for the positive eigenvalues and -1 for the negative eigenvalues. And to regularize, you can multiply by lambda to minus s, and then you continue analytically to s equal to 0. So this is the partition function of our non-trivial phase, which I'll call z of the p+ip superconductor. Now this object, unlike the case of the Kitaev chain, turns out not to be a topological, strictly speaking, a topological invariant. This object depends on the metric that you put on your manifold and to which the Majorana is coupled. So let's write that down. Maybe I'll go here. It is dependent on the mass, but it's just that the mass dependence is local counter terms. You can actually calculate it in some power series in 1 over m. You can compute kind of using heat kernel type methods. So eta is not a top. So eta depends on the metric, on your manifold, on G mu nu. Now there is a nice expression for eta, which you can obtain again using the Ataya-Patodi-Zinger theorem. And it says that eta of this Dirac operator, 24 pi squared m4 Let me explain this formula. So what the Ataya-Patodi-Zinger theorem tells you is that suppose we have our system on a three-dimensional manifold X3 with some metric, and there is also a spin structure chosen, right? Because this Dirac operator will depend on the spin structure. And suppose I extend the 3-manifold to a 4-manifold, preserving the spin structure, kind of continuing the spin structure. Then on this 4-manifold, I calculate the integral of this R wedge R, where R is the Riemann tensor. I calculate it on this M4, which is a manifold with a boundary. Claim is that that's related to the spectral asymmetry of the Dirac operator on the boundary. Now, this R wedge R is basically a total derivative. So if I am not careful, I can rewrite this object as, in terms of the spin connection on the boundary, as something like this. The omega but this is not a globally defined expression. So to really make sense of it, I should think of it in this way by continuing to a 4-manifold. So this whole expression I'll write as e to the I Chern Simons gravitational of my manifold and the spin. There are too many eters. Let me call it sigma, the spin connection. And this gravitational Chern Simons is defined by the continuation to a 4-dimensional manifold. Now you can ask, okay, what if I choose two different continuations to two different manifolds, continuing the spin structure? Do I get the same answer? Well, by the APS theorem, you must. And there is a simple, the way to see that is, suppose I continue to M4 and I continue to M4 prime. And then I can consider the difference of the two, or the ratio of the two partition functions, or two integrals here. And, well, that corresponds to the integral of this object on a closed manifold. And now on a closed manifold, it turns out that this -1 over 24 pi squared trace R wedge R is equal to the signature of the manifold. So let me write not M, but let me write Y4 for Y4 closed. Now for a smooth 4-dimensional spin manifold, the signature is always a multiple of 16. This is so-called Rochlin's theorem, and the simplest proof is actually through this Ataya-Zinger theorem, which is kind of the version of the Ataya-Patodi-Zinger theorem, but without the boundary. So then you see that, if this quantity is a multiple of 16, then the difference, or the ratio of partition functions that I get by extending to different manifolds M4 and M4 prime is always going to be, the phase is always going to be 2 pi over 16 times a multiple of 16. So it's always going to be a trivial phase. Okay. So let's see, where do we go? So what this theory gives me is an invertible phase in 2 + 1 dimension, but one where the partition function, at least in the continuum, depends on the metric. So Zp plus Ip, invertible phase of fermions in 2 + 1D. Now, we see that this 2 + 1D phase is related to a topological invariant, the signature of 4-dimensional manifolds. It turns out that the signature is also not only a topological invariant of closed 4-dimensional manifolds, but also a bordism invariant. Sigma signature, sigma of Y4 is a bordism invariant itself. It's actually easy to see that you just take D of trace R wedge R and you get 0. So because it's a closed form, so you can trivially, it's a bordism invariant. So this is interesting. Okay, so further, I'll just write that the bordism group of spin manifolds in 4 dimensions is integers generated by the K3 surface that Thomas already alluded to. So you see now that these invertible phases of fermions in 2 + 1 dimensions are classified, are related to the bordism group in 1 higher dimension. So general belief is that if you want all the invertible phases in D dimensions are in 1-to-1 correspondence with the torsion group of bordism, with the torsion of the bordism group in D dimensions plus the free part in D + 1 dimensions. And this free part is kind of simpler than this torsion part. So this free part corresponds to just Chern Simons terms. So this particular case was the gravitational Chern Simons in 2 + 1D. So this is Chern Simons terms in D dimensions. And these ones, if you think of the boundary of the D-dimensional theory, these give you the usual kind of local perturbative anomalies, either gravitational or symmetry Toft anomalies. These ones, if you look at the boundary, give you the discrete anomalies, the non-perturbative anomalies. Okay. Let's see, how am I doing on time? I have 10 minutes left. All right. So any questions at this point? Yes?
So do you have this thing in all like 2 + 1D, 4 + 1D? Like, is it every 2 dimensions? Do you have some Z invariants?
I think that, at least for bosons, I think the Z invariants are in dimensions which are multiples of 4, if I'm not mistaken. Maybe someone can.
No, if you have an abelian.
No, I'm talking about gravitational. Yeah.
I got confused. Why is the partition function of this p+ip related to the signature of a closed Bordism manifold?
Well, so this was the partition function that we derived from the Majorana, massive Majorana, right? It was this eta invariant. The eta invariant is related to integral of trace r wedge r over a four-dimensional manifold with a boundary. Now, for this extension to be unique, the integral of this object on a closed manifold has to be quantized. And that quantized number is the Bordism invariant of a four-dimensional manifold. Yeah.
First question?
Yeah.
Is that what people sometimes call the Anderson dual of the group, as opposed to the Chern dual?
Is it? Okay, someone is nodding, so I guess. You mean you mean the sum? You mean the sum of the torsion and the? Yeah. Okay, so I gave you all these nice examples of Bordism groups, and I connected them with kind of physical arguments. But why should Bordism classify invertible phases? That's the somewhat mysterious at this point. And next I want to sketch, if my iPad can go back to where I want. Okay, so why should partition function of a topological quantum field theory, which is invertible, be a Bordism invariant? And I guess I'll maybe start today and continue tomorrow. So suppose we consider invertible TQFTs. That is, invertible and partition function is metric independent. That will be the assumption. So we are not going to consider these phases that are related to Chern Simons terms. And I'm going to make the following statement. For an invertible TQFT that satisfies for an invertible unitarity will be important here, unitary TQFT that satisfies with partition function on the D sphere. So this TQFT in D dimensions with the partition function on the D sphere equal to 1. The partition function is a Bordism invariant. So this is a theorem by Moore and Fried. And if you want kind of a more detailed discussion, then I recommend this article by Yonekura. So we're going to give an argument in favor of this. And the point is the following. So suppose I take a Bordism claim is that this bordism can be decomposed into surgery operations on my d-dimensional manifold. So the idea is that you think about this bordism and you kind of follow it, and up to a certain point if you think of this as kind of some evolution with some parameter, I'm going to slice my d+1 dimensional manifold through in some way up to some slice. Everything is homotopy equivalent, and then at some point right here, there is a singularity. The manifold evolves discontinuously, and we are going to characterize precisely this jump of the manifold topology, and turns out that this jump will be related to surgery. So what is surgery? Surgery is suppose you take a manifold xd and you remove from it first the following d-dimensional manifold, and then you glue back a different d+1 dimensional manifold. Both of these manifolds have a boundary, and the boundary is the same. So the boundary of SP cross d minus p is the same as the boundary of this manifold. So you glue back along that boundary, and the boundary is nothing but SP cross S d minus p minus 1. So in the simplest example that we have here, we start with a circle, right? That's our manifold xd. Let's choose p equal 0, d is equal to 1, right? The manifolds have dimension 1. So S naught cross d1 is 2 segments. So I cut out 2 segments from here, and then I glue back d1 cross S naught. Again, 2 segments, but if you think about how they're glued, then they're glued union d1 cross S naught. They're precisely these 2 segments going into here. So then you get 2 circles. So the claim is that any bordism can be decomposed into sequences of such surgery operations. And then you can show that under surgery, the partition function remains invariant, assuming that the partition function of a sphere is 1 and that your TQ-FT is unitary. So maybe we'll flesh that out in some detail next time. Yeah, so this proves that if you have a and invertibility is very important. We'll see where invertibility comes in. So the fact that we'll use the fact that the ground state on any spatial manifold is unique. That's remember a property of invertible TQ-FTs. So let's continue next time.
How should I think about this assumption that partition function on the sphere is equal to 1?
Actually, we'll see next time that if d is odd, this is automatic for an invertible unitary TQ-FT. If d is even, then you can add a counter term, which is just the Euler density, that will make sure that this assumption is satisfied. So in fact, up to local counter terms, you always have this property.
About this property, in two-dimensional BF theory level 1, which is invertible.
Two-dimensional BF theory level 1.
Okay. Two-dimensional, yeah, 1 plus 1. There are some weird claims that this thing is infinity or zero, or there are some very weird claims that are very contradictory to one.
Well, it's obtained by S2, right? Is obtained by gluing two disks, right? And you assume that on a okay, actually, you have to assume that the state that you generate is non-zero. That's maybe a non-trivial. Okay, maybe you need to. Maybe there is an extra assumption that z of SD is not equal to 0. Oh, then this. Well, what if the state that you?
No, because you can cut this here in two, and the two have like an inner product. Right?
Yeah. What if the state that you produce is 0?
Yeah, but the partition function on unitary implies that z of SD is strictly positive in the unitary theory.
Oh, because the circle has. The circle must have a ground. Must have. What if the state you produce is 0?
Well, then if the hemisphere state is 0, then the other hemisphere also is 0, and the inner product is 0.
Yeah.
Can't see that.
Well, inner product can be 0, right? So the claim is
Is it Euclidean sphere or a spatial sphere?
Euclidean. But suppose I generate a state, right, on a circle by doing this path integral on a disk,
yeah.
right? The question is whether that state can be 0.
No. Just as an example, in any 2+1D modular tensor category, the partition function is S00, the 0, element of the modular S matrix.
Yes.
It's strictly positive.
So maybe we can somehow argue that relate this to ground state on S1.
You don't need that, I think.
Well, the question is, you take this, you take this,
yeah.
but you calculate this path integral.
Right.
It produces a state.
So then you're using unitarity in the guise of reflection positivity to tell you that the reflection positive friend of this state is the state that you would have generated from the other hemisphere.
Yes.
Then you have the norm of the state.
Yeah, what if the state is 0?
Not in a unitary theory. That can't happen in a unitary theory. So can it happen?
0 vector has 0.
0 vector has 0.
No, but you're not putting any insertion into this.
Yeah. I'm going to think about it and try to give you an answer next time.